Okay, so welcome back to another video. So here we have a infinite limit, and it's also combined with that we have nested radicals of the trigonometrics functions. So we have that n squared multiplied by the square root of 1 minus cosine of 1 over n. Inside that nested radical is the same thing, square root of 1 minus cosine 1 over 1n. And the same thing repeats. Again, the term is nested. So you probably might be thinking that if we were to treat this like as some sort of equation, for example, if we were to set y equals, I'm just saying a letter, for example, y equals some radical and then put something in another variable so that it repeats itself. Well, we can go into that approach if we want to, but we don't really need to do that, because if we actually use the properties of exponents, there's actually another way to actually rewrite this whole limit in, a completely easier expression. And not only that, with limits, there's also some properties that you might see that eventually that you might think it's in terms of L'Hopital's rule, but I'm just going to give the, disclaimer and say that L'Hopital's rule will not be used. Instead, there's actually another property that we'll be using for limits that's, the most important limit that especially you learn in calculus that we will be utilizing to help evaluate this entire thing. So nothing more to it. This is actually not really a difficult problem, but I also think it was a cool problem to actually show to the internet. So why don't we just get started? So if we take a look at this nested radical expression, so let me actually write this out in full before I go into the details. So as we see that everything is nested, we can actually write this in terms of, the exponent. So specifically, since everything is entirely under the square root, so the exponent's 1/2, then we can actually put this under 1/2 as well, and 1/2, but we're just multiplying with exponents. So in other words, if we put this all together, so specifically we would have the product written as follows. So we have 1 minus cosine of 1 over n to the power 1/2. Then we multiply by the same thing, except this time, since it's completely nested, so it's actually double, well, really multiply from the denominator specifically. So this will be multiplied with 1 over, the exponent's 1 over 4. Then same thing, except do this again, but except this is going to be 1 to the power, or 1/8, and this keeps going. So of course, if we know that this is under the same base, then we can actually use the rules of exponents and add these exponents up together. So 1 minus cosine of 1 divided by n, then to the power 1/2, add this with 1 over 4, add this with 1 over 8, keep going so on and so forth. Then interestingly, we know that the exponent sum is, if you take a look closely, this is actually in the form of a geometric series with the ratio of 1/2. And our index starts at 1 if you take a look at a closer inspection. So be careful on how you use the closed form formula for the geometric series. Instead, it's your starting ratio, which is 1/2 divided by 1 minus your ratio 1/2, and then that means the exponent's 1. It's not 1 divided by 1 minus the ratio. Otherwise, that would have to mean that the index would have to start at 0. But here, this is completely different. So that means this entire exponent is actually going to converge to 1, and so therefore this entire base is just going to be by itself. So 1 minus cosine of 1 divided by n. So this means that this actually makes writing this expression a little bit easier and a little bit, it is easier to evaluate in a sense. So here we're gonna rewrite this expression. So I'm gonna call this whole limit that we're given capital L. So the limit as n approaches infinity. So now we have n squared, and then just the base itself. The radicals is completely out of our, out of question. So there we have it. And so now we're actually using a little bit of trigonometry, some trigonometric formula. Specifically, the power reduction formula says that if we have sine square of x, this is going to equal to 1 minus cosine of 2x, and then we divide this by 2. So if we were to solve this out by itself, really because we have a in a form of a 1 minus cosine some input, so we treat it in that sense. So that means we're going to have 2 times sine square of x, and let this equal to 1 minus cosine of 2x. Okay, so some form over here is simply related, but we just have to choose the correct inputs that we want to put in. So in this situation, if we have that 2x has to equal 1 over n, so what will be the input for over here? Well, really, it's if we solve this out, simply we see that 1 minus cosine of 1 divided by n. If we choose, if we're choosing this input, so we have to find what this input is over here. So we'll have that this is going to equal to 2 times sine square of 1 divided by 2n. And so with that, now we can actually just plug this back into our, our L. So L equals the new rewritten limit as n approaches infinity. Okay, so first we have a 2, so let me actually put that outside of our limit. That's just a constant. So 2 times the limit as n approaches infinity of n squared, then multiplied by sine square of 1 divided by 2n. Okay, so if we were to take that limit, otherwise we see that this is actually just going to give, the entire thing's infinity. So you might be thinking, okay, how's this, can we convert this to L'Hopital's rule? Now I said that that's not going to happen, but if we actually rewrite this in the form of a, rational function, so we have 2 times the limit as n approaches infinity. So the numerator in this situation is going to be sine square of 1 divided by 2n, and our denominator, we're going to write this that's such that it's equivalent. So this will be 1 divided by n squared. Why can't we use L'Hopital's rule? If you notice that we keep getting like the indeterminate form, specifically this we have a 0 over 0. So as we see that if we were to differentiate this, this is actually continuously differentiable. So no matter how many times you keep doing this, you're always going to keep getting the indeterminate form and not some sort of finite value. You can even see this for your, you can actually do the calculations yourself and see that the method is not going to really get you to what you want. No worries. There's a little bit of rewriting that we can put, and that is what I can do is I'll multiply a 1 over 4 to both the numerator and denominator. So what this means that this 2 will now become a 1/2. And then if I multiply the 1 over 4 in the bottom, so I have a 1 over 4n squared, but I can actually rewrite that as a different quantity and put that as quantity squared. So here we have that the limit as n approaches infinity. So the numerator still stays the same. Meanwhile, the bottom now becomes 1 divided by 2 to the power n, and then quantity square. Interestingly, we have 2 of the same inputs. So here's a little bit on what we can do here, because we still can't really take the we can't take L'Hopital's rule. Not still, we can't, because again, it's still continuously differentiable. You're just not going to get anywhere with it, finitely speaking. So what we can do is we can actually do a little bit of a variable substitution. So I'm going to let u equals 1 divided by 2n. Okay, so now we actually have a new limit. So let's see, I have a 1/2 outside over here. But if I put this for n approaches infinity, that means u is going to tend towards 0. And we have sine square of u, and then divided by u squared. And then here's a little note that I'm sure all you guys remember, this little property from your standard calculus 1 class. And that says that specifically the limit as u approaches 0, we're going to use that variable. U approaches 0 of sine of u divided by u is actually just going to equal 1. So this method can work here as well, because this is basically just taking that square. And so that means this is just 1/2 multiplied by 1 squared, which is just equal to 1/2. And so therefore, that actually completes the evaluation of our given limit over here. So yeah, pretty cool nested trigonometric limit, if I say so myself. And there's not too much going on to it. So yeah, that's pretty cool if you ask me.